So as I said, I'll prove only the statement 1, and 1 will immediately imply, under the assumption of this theorem, 2 and 3 also. Okay. So we know that a positive recurrent irreducible Markov chain has unique stationary distribution, and the stationary distribution satisfies is positive everywhere for each chains in S. So that both of these statements will actually follow from the previous theorem. We just go back to the theorem and its proof, and that will show that this is indeed the case. So anyway, so we'll prove 1 here. So namely, we'll prove that if you start with an irreducible Markov chain, which has a stationary distribution, then that Markov chain has to be positive recurrent. So this is what we want to show. So positive recurrent means, of course, in particular, it's recurrent. We will first show that it is recurrent, and then we'll show it is positive recurrent. And we'll see why first showing recurrence will help. We'll see that. Okay. Suppose it is not recurrent, then of course it has to be transient because there's an irreducible Markov chain. Either it's a recurrent Markov chain or it is a transient Markov chain, because recurrence and transients are both class properties. So therefore, assume that this Markov chain is transient. Now, transience means that for all states I and j, Pijn's, this will converge to 0 as n goes to infinity. This is something we have proved already. Now, from this limit, using the fact that Pij equals Pij times Pijn also, Pij equals the sum of pi times Pijn I runs over S, right? Because pi transpose equal to pi transpose times P, repeated application will tell you that pi transpose equal to pi transpose times Pn, P power n, and that will give you this equality. Using star and this equality and dominated convergence theorem, show that each Pij is going to each of these quantity is going to converge to 0. In particular, this will mean that each Pij is 0, which contradicts the fact that sum of the Pij's equals 1. And of course, where is the contradiction coming from? It's coming from the fact that we had assumed the Markov chain to be transient. So therefore, the Markov chain has to be recurrent. This shows that the Markov chain is recurrent modulo this exercise. Okay? Show that this convergence immediately implies, by dominated convergence theorem, that each of this sum is going to 0 also. So basically, if this goes to 0, then each of these sums are going to 0. And then this is where we are using the fact that pi I, as I runs over S, is indeed a probability distribution. Okay? So define random variables that take these values. Okay? And then define the probability to be this pi i's. So therefore, this becomes the expectation. And then expectation of the limit is the limit of the expectation. So limit of the expectation would be expectation of the limits, and limit is 0. So therefore, expectation of the limit is 0. Therefore, limit of the expectation would also be 0. Of course, you have to show that dominated convergence theorems can be applied, but here everything is bounded by 1. So we are actually using bounded convergence theorem. But do finish it yourself. Do convince yourself that dominated convergence theorem, or more precisely, bounded convergence theorem, can be applied from star to get to this contradiction. Namely, each pi j equals 0, which of course contradicts the fact that summation pi j is 1. Okay? So therefore, with the help of this exercise, what we have shown is that this Markov chain is already, it was irreducible, it's actually recurrent. Now we'll show it is positive recurrent. So we have already shown it is recurrent. The moment it is recurrent, just fix an I in S, fix a state. It's obviously is a recurrent state. Since it's a recurrent state, we get an invariant measure, nu, where nu j is basically the number of hits to the state j by the Markov chain between 2 hits to the state I. So in other words, if you start the Markov chain at I, you look at the first excursion. In the first excursion, what is the expected number of hits to the state G? So that's your new chain. And we have shown that if the Markov chain is irreducible and recurrent, then this is actually strictly positive and finite also. And this gives an invariant measure for the Markov chain. We are also given another invariant measure, namely the stationary distribution pi. Okay? We know when the Markov chain is irreducible and recurrent, then any two invariant measures are essentially a constant multiple of the other. Okay? So basically one invariant measure would be a scalar multiple of the other. And of course we know that this nu is non-zero also. All the nu j's are positive. That also we proved under irreducibility. So therefore there exists a strictly positive scalar C such that each nu j is equal to C times pi j. So this is from the, again, the theorem that we have proved last time. I think last time, yeah. We have this theorem we have proved, right? If you have an irreducible Markov chain and recurrent, then we know that the invariant measure is unique up to a constant multiple. The constant can be zero also, but in this case that is not allowed because these nu j's are strictly positive. So therefore, you have this thing. So we started with a Markov chain which is irreducible, which has a stationary distribution. We fixed a state I and showed that expected, starting from the state I, expected number of hittings of the state J in the first excursion to the state I. This guy, this expectation is actually constant times pi j for each state J for some C positive. Okay, so this is what we have shown so far using the previous theorem. Now we are in a position to show that the state is actually positive recurrent. The Markov chain is actually positive recurrent. We'll first show that the state I is positive recurrent. And that's enough because of irreducibility. But let's first show that. So therefore we get C is finite and C is also the sum of the nu j's, right? Because sum of the nu j's is C times sum of the pi j's and sum of the pi j is equal to 1. Right? So therefore, this sum is equal to C, which is finite. Now, what is this sum? This sum, if you just write longhand, is just sum of these guys. We just put the values of each nu j. Now, of course, everything is non-negative, and we know if you have non-negative random variables, then expectation of a sum is the sum of the expectations, even if it's a countable sum. That follows from monotone convergence theorem. So therefore, the sum can go inside the expectation. And also, once it goes inside the expectation, we have done it many times. Since everything is non-negative, we can interchange the sum also. So by taking the sum inside the expectation and then interchanging the sum by Fubini, what we get is this thing. This is the expectation starting from I of this quantity. Now we have done this calculation before, so I'm going to go through this fast. We know that for every, so what's the advantage of interchanging the sum? The advantage is that for every fixed n, xn will be exactly one particular state, right? So therefore, this is always 1. Exactly one of these indicators will be 1. All the other indicators would be 0. So therefore, this sum is going to give you 1 all the time because you're just saying this sum is basically only the value that xn takes, it will give you for that particular j, this will be 1. All the other ones will give you 0. Therefore, this is always 1. This sum inside. So therefore, this is sum of 1. How many ones are there? Tau I1 many. So therefore, this is the expectation of tau I1. And that in turn, therefore, is positive, is finite. So therefore, what we have shown, that starting from an irreducible Markov chain, which has a stationary distribution pi, we have shown that fixing a state I, we have shown that this I is positive recurrent. Namely, starting from I, the return time to I has finite expectation. The first return time to I has finite expectation. So this shows that I is positive recurrent, and hence by irreducibility of the chain, Xn is a positive recurrent Markov chain. Namely, What I'm saying is that since positive recurrence is a class property, this will immediately tell you that this whole Markov chain, all the states are positive recurrent, and this is a positive recurrent Markov chain, in other words. So this completes the proof of one. So this tells you that if you start with a Markov chain which is irreducible and it has a stationary distribution pi, then it has to be positive recurrent. And therefore, the stationary distribution pi has to be unique. The stationary distribution is unique. It has to equal this pi that is given. And of course, all the pi j's are going to be strictly positive as well as a fallout of this. So this proves the first three parts of the theorem. Next time, we'll prove the fourth part. Let's quickly go back and check where we stand. So we have already proved one, the first part, which already implies 2 and 3. So therefore, we have proved 1, 2, and 3. Now we'll prove the fourth part, which is essentially saying, if you have an irreducible, positive recurrent and aperiodic Markov chain, then the unique stationary distribution is the limiting distribution of the chain. And proof of this is going to be totally different from all the proofs we have done so far. It's going to use a very sophisticated probabilistic technique called the coupling technique. And I'll introduce it in the next class. And as far as results are concerned, for your final examination, this is the syllabus. No new result will be introduced. Next time, then we'll just prove this theorem, the fourth part of this theorem. Okay, so this is where we stop today.